Okay, um, welcome everyone. We are going to switch back to AI hardware. We were very secure now, so we can securely go to AI hardware. Um, we are going to have another assignment is going to come during lunch to not mess up with your enjoyment of the food. But hopefully it's going to be also a learning experience like the previous ones. Today we are going to wrap up, in some sense, this, general AI kind of in the cloud and things like that. And tomorrow we are going to go to the even more, I mean, this is a little bit hands-on, but not really. You'll have your hands on your laptops. The computation is still somewhere in the cloud. Tomorrow we are going to start playing with the hardware. So we'll see, that's going to be a little bit more challenging because of the number of students, and also unfortunately for the people online, they are probably, again, I talked to some of the IIT students that are helping, probably will have a demo with a camera online to kind of get the experience of virtually hands-on experience. There's going to be some lecturing now before lunch, then we'll have lunch, and then we'll have a little bit more lecturing. In the little bit more lecturing is when I'm going to ask for, some voting on, which platform maybe we should go over. But this one, I was, I was thinking about, starting the voting right now, but I think it is important to go over this one specific one because it's been a very seminal contribution to AI hardware from a professor at MIT, Vivian Zee. And, it's a chip, so that should relate to, many people in the audience. It's a relatively small chip, so it's 4 by 4 millimeters. And it's relatively old by now. It's, 9 years old, I guess, by now. But again, it's been quite influential. And the reason it's been quite influential, and you'll see in the presentation, is that it's not, okay, I designed this chip, and and I measured it, and it runs this fast, and it consumes this much power. It's it's the whole process of designing and optimizing the chip that when you see it, it kind of hopefully is going to make you understand why. And again, it's not just about the chip. Is really the path taken, and that path includes, a taxonomy. So, this is a word that you'll see come quite often. Basically, when you have a design space, being able to have classes of different solutions and, comparing them qualitatively at first and then quantitatively is very important. And then again, you see, we talked yesterday about optimization. So you compare the energy efficiency of different data flow under the same area and setup. So these are, remember, you have to optimize something. So you optimize the energy efficiency under some constraints. So, you cannot, again, the constraint was you have some fixed area. And, the results here are basically 35 frames per second, with some hundreds of milliwatts of power. And this is for AlexNet type computation, which AlexNet is, that one that we talked about yesterday. So again, this is about, if we had a paper, and there are going to be papers like this, more modern in 2025. They are probably going to be about transformer models. At the time, convolution, the Gartner hype. So convolutional neural networks were on the hype regime. Now convolutional neural networks are in the mature part, and there are others in the hype regime. But again, it's important to understand the the context. So basically, again, you have these convolutional neural layers, and the features. So we talked yesterday about how the features changed, and there was some controversy about the sizes and all that. But independent of that, you have this progression of simpler features on the input and more complex features on the output. And at some point, you still have a fully connected layer. This is like the original perceptron that we talked about in the first lecture, where you look at the output of the last layer of features and you make the best guess, you being the CNN, make the best guess about which, are you looking at a bird, at a cat, at a dog, or whatever, depending on what classes you have there. So this is, and again, some of the modern ones are very deep here, hundreds or even thousands of. So now if you look at the real computation that goes on, you have, these convolutional layers. And again, there are thousands of them. You have a fully connected layer at the end. But convolutions are basically dominating everything. And again, a quick recap. You have this concept of a filter or a kernel, it's sometimes called. And you basically multiply and add across an area of your image, and then you get just one output, which becomes a pixel in the next image. And you keep doing it like that. And what makes it computationally intensive is that you have many channels, and that everything gets multiplied, and you also have multiple kernels, and you also have multiple images, and again, multiple means very large number. So at the end of the day, everything is multiplicative. So you really have a really large number. So if you, and again, we are back kind of to the memory wall. So if you look at, if you just do, if you have a processing element that does the multiply and add, the MAC, you need to take the input pixel and you multiply it by the weight, the kernel or filter weight. And then you need to add that to the, again, it's a multiply and add with the, with the sigma, with the sum. So you accumulate this sum. So, you have that for loop, and so there is some preliminary sum, and then you add another, and you get the updated partial sum, and this basically goes back on the input for the next iteration. So this would be, kind of the fundamental building block. Now, the simplest, implementation would be to have everything in main memory, in kind of a DRAM. If you were to do it this way, you basically, again, for a very old type of convolutional neural networks, again, 13 years old by now, this is the one that, kind of revolutionized AI. But again, it's really old, so really small in the big scheme of things. And even this one has, 724 million, MAC operations. And then if you were to take, you have 3 each reads from memory and 1 write to memory. So that gives you, almost 3 billion DRAM accesses, so that definitely, wouldn't work. And again, this presentation, and, this is how Vivian Z. So this is not mine. This is, from her slides. But, it's basically kind of reintroducing the concept of memory hierarchy, kind of, and justifying it. So you basically want to have, some caches. That's the bottom line, because without that, you'll do very bad. And once you have the caches, what you hope for is to reuse the data from that cache. Again, hopefully most of you have taken a computer architecture class. You know that for caches to be effective, you need to have locality, right? So you need to have either spatial locality. So if I access, a data somewhere in memory, it should be relatively high probability that I'm going to access something next to that data. And that's data, spatial locality. So then you can get, when you take one element from memory, you can take, many of them together. And with high probability, you are going to reuse those. Or temporal locality. If I'm using some data, at some clock cycle, some time t, it should be relatively high probability that, in the next few cycles, I'm going to access that data again. And if that's the case, then, these memories help. If you only access it one at a time and not at all after that, then this wouldn't help. But again, data reuse is an important part. And there are several types of reuse that you can have. So basically, one is that your kernel that you are applying over the image stays the same as you slide it across the image. So that's reuse. If I have that, kernel or filter in the cache, in the local memory, then, I don't need to go to the main memory. I can reuse it from there. Another one is if I have the image in the local memory. So I can have the image in the local memory, and as I have multiple filters, multiple kernels that need to go over that image, again, there is data reuse. And, the other basically would be where you reuse the, well, let me see. So here, I guess, this is just for the convolutional layers, and here is for the fully connected layer. But, basically, here you can reuse both the image and the filter because, again, the convolution goes like that. Here, because, again, you are in the fully connected layer, you are just reusing the filter weights. And again, just having this cache, you reduce the main memory accesses by 500x, which is quite significant. It's almost 3 orders of magnitude. So, this is the kind of the other kind of opportunity for reuse is the fact that when you do the accumulation, you can accumulate just in this memory, and you don't need to access. So this is everything, here is about the input, but you have also an opportunity to reuse the data on the output. And by using both of these, again, you go from 3 billion to only 61 million accesses to DRAM. Now, let me see. Give me 1 second. Okay. So the next kind of innovation is to have, and this should be obvious because we want parallelism, is to have instead of just one. So until now, we basically reinvented the CPU. Until now, it was really a reinvention of the CPU because you do just one operation at a time. You reduce the memory accesses, but you don't really speed up the computation in terms of the number of actual compute cycles. So you need some kind of parallelism, and again, the one possibility, which is so again, we haven't really discussed about the TPU. We discussed about the GPU a little bit about what's going on inside the GPU. So this discussion would have made more sense if we had discussed a little bit about the TPU. But the idea, well, we discussed a little bit about coarse grain reconfigurable arrays. So maybe that's one way to kind of understand what's going on here. So if you think about an FPGA or some kind of spatial hardware, is very different from a CPU and from a GPU in some sense, because the computation happens spatially. Okay, so it's really like a circuit. All of you are, or most of you are circuit designers. So in a circuit, you have gates and you have wires, and basically you do an and then the output goes to the next gate, and maybe there you do an add, and then it goes to the next gate, and there you do some multiply, and then you put into a register, and you have maybe pipelining and things like that. So everything happens in space, spatially, which is very different, again, from a CPU that runs software where, everything happens kind of in time. So this spatial thing is, and that's why I wanted to have this, discussion today, because until now it was, although we are talking about AI hardware, it was kind of still, more of the software designers' way of thinking. But here is really hardware, because again, we have processing elements, and they do a computation, and then the result goes to the next processing element, and so on and so forth. So, and you see that you have, and a coarse grain reconfigurable array basically is based on this same concept. So you have processing elements, and you have connectivity. In this case, the connectivity is relatively limited. It's just basically the nearest neighbor, east, west, south, north, south. In a more general coarse grain reconfigurable array, the connectivity is more complex. You have what's called a network on chip. And in principle, this processor can talk to that processor by sending a packet. So again, I hope I'm not confusing you, but because we don't have time to go over all these concepts, I kind of want to cram them here. But basically, this is, kind of the generic AI accelerator architecture that, this Iris proposes. So you have a two-dimensional array of processing elements with some local memory, basically a register file, with some control, and that can each of them do a multiply add kind of operation. And then, data can move horizontally, vertically, and then there is some kind of a cache here, this global buffer, and then there is the main memory. And what can move in between these processing elements, it's anything that we had on the previous slide, which is inputs, the image, the partial sums, and and the partial sums, because the partial sums are both inputs and outputs. So any questions? Yeah, I would like to have questions now. Yeah. Yes?
Like how these ALUs are working, like bottom to top or left to right or something?
Well, so right now this is generic. So that's going to be the next discussion, for the rest of the time. So this is generic. They can move in any way. Now, this is the design space exploration that we are talking about. So this defines your kind of, your building blocks. Now, how you use them is going to make the performance quite different. You can use them in a bad way, in a suboptimal way, and most of them would be, for example, idle and waiting for data, or some of them would have too much data and they would kind of keep everything bottlenecked. So doing the data flow, that's what's called. So basically how data moves, that's the key to this architecture. And, and that's what, you are going to see. So there are many options, actually. That's the interesting thing. So again, this is a very, very general kind of idea. And yeah. Any other questions? Yeah.
For this particular architecture, I believe the time to the first output will be higher, because to get the data to the last row ALU, it will take me at least 4 clock cycle or something, and to get the data out from that ALU again to the buffer, again it is going to take the 4 clock cycles, right? So the time to the first output, that is the latency, will be higher using this architecture.
So remember, we talked about this yesterday relatively at length, latency versus throughput. For AI, latency, well, I shouldn't say latency doesn't matter, but latency doesn't matter. No, because that's why we use GPUs and not CPUs. Because if you care about latency, we should always use CPUs. They have the lowest latency. But also not enough throughput. So if you only care about the first output, the first data, all these AI, you're right, but the point is it doesn't matter. Because what really matters, you saw there were 3 billion memory accesses. Yeah, I don't care what happens until the first memory access. No one cares. I care about what happens for the 3 billionth one. And in order to make the delay to the 3 billionth one shorter, it's important to have high throughput. It's important to keep all these things busy all the time. Yeah, as long as they are busy and they don't do redundant computations, you're golden. So yeah, other comments, questions, anything online, if there are, please check the chat box. Okay, so yeah, so let's see how this goes. So yeah, so I think we talked about everything that's on this slide. Okay, so oh yeah, okay. So now we go a little bit kind of inside this, to have a comparison. So to have a comparison, you need to understand, and again, this iris was not as much about performance, and it was because, again, it was more for kind of edge applications, so it was more about energy. So in terms of energy, the energy for, and again, I hope that for you this is not surprising, but for kind of, junior students, when they first, they first see this, I think they are very surprised. And again, historically, this was not true. If you look back 20 years ago, this was not true. But nowadays, because of the way technology has evolved, the actual compute is the least expensive. Doing an ALU, add, multiply, is the least expensive, and any kind of memory much more expensive. So again, this is an important, and it's part of the memory. But again, if you take as the energy of one MAC operation versus the energy of accessing the register file, that's another one. Then if you look at and again, there are these, and if there is this network on chip, and there is this processing, that's a little bit more. Then the buffer, which is the cache, that's 6 times, and then the main memory is like 200 times more expensive. So saving one memory access is equivalent to 600 compute operations. So this is basically what we were just talking about, is that you need to, in order to get the advantages of this data reuse and the register file and all that, you really need to have good control over the data flow. How, exactly what you guys were asking about. How does the how do the inputs move left, right, up, down, and things like that. So there are a few, and this is the important part. Maybe some of you have already heard these terms, but I think this is the important part. So now you have some choices in the design space exploration, okay? And one choice is to have what's called a weight stationary data flow. So weight stationary means that in each of these processing elements, I keep the weight local in the register file. So again, if you think about convolutional neural network kernel, so one kernel, let's say if it's 4 pixels, you would have that kernel, local, and all of them would be basically in these processing elements. And then the only thing that needs to come in that processing element is the input, the pixel from the input, and the partial sum, so that you can get the next, you can add the product basically of the pixel times the weights of the kernel to this partial sum, and then basically you see that the partial sum comes from the buffer, and then you multiply the first weight with the first pixel, then you multiply with the second weight, with the third weight, the fourth weight, and you do the accumulation. So you see how again, in that array, the information needs to move this way. So you need to have the pixels come into the processing elements, and then have the partial sum. And once the partial sum, once you do all the max, then the partial sum goes back into the global buffer. So again, this, and what she's doing now, so again, remember the first slide about the taxonomy. So now basically she's showing how this generic, like I said, this is a very generic architecture, just with processing elements and the two-dimensional connectivity, how it relates to existing solutions that were published at the time. So there are these papers. So any questions about this? Yeah.
Can you make open internet CNN, it can help fully connected layer, NAC, and convolutional layer, NAC, both.
Okay, you need to say it a little bit, slow. Yeah. Yeah, yeah, yeah. Okay, let me see. Yeah, yeah. Don't see it. So how did you get it if it's not here? Oh, maybe. Okay. Oh, it was directly to Sachin. Okay. Okay. Yeah.
Copy and paste.
Yeah, can you send it to everyone? So can we make common internal architecture inside CNN, which can hold fully connected layer and convolution? I'm not sure that I fully understand the question, but yes, these these array kind of architectures do support also fully connected layers, except that they are going to be, again, they are really targeting convolutional neural network, convolutional layers, because convolutional layers, are many more than the fully connected at the end, at least for, the traditional deep convolutional neural networks. But yes, definitely the computation would happen still here. It wouldn't be so, efficient. There would be more waste in the weight, again, this weight stationary and the others that we are going to see, maybe they do not really apply. But again, this is a very general purpose kind of, in the worst case, you can do just one processing element at a time and you can do any computation. So it's not that if it can be done, the question is a little bit maybe about efficiency. So probably it's going to be less efficient for fully connected. I hope that I understood the question and that this answer is, good enough, so to speak. But yeah, so another option is to have what's called output stationary. So output really means the partial products. So those are the outputs. So if the outputs are stationary, then what's going to move in the array are the inputs and the weights. So and again, this kind of data flow shows that. So you basically have the input pixel that comes from the cache, and then that's being transferred, to all these. So now inside here, you have the full kernel, the full filter in one of these processing elements, and basically does this partial sum. No, I'm sorry, no, the weights are still coming from the outside, but this will be the one pixel. So basically, each of these is going to be one output pixel. So this is the pixel 0, this is pixel 1, this is pixel 2, and pixel 3. And basically, to calculate pixel 0, again, you need to take all the weights of the filter, multiply by all the pixels in the image, and then you get one pixel on the output. So that's how this data flow looks like. So here again, you minimize the read-write for the partial sum. And again, there are some examples of existing, kind of custom accelerators that are doing that kind of data flow. And again, that's why I wanted to show you these slides, because again, it covers really a large array of possible accelerators that had been published, and hopefully it's going to be useful. And then another possibility is to not have a register file in each processing element. So if you don't have a register file, in some sense, you need to go to, not to the main memory, but to this global kind of cache for everything. And you shouldn't be surprised that this, in principle, is going to be less efficient, energy efficient, because, without having any kind of local, low cost memory, you need much more data to move. So you see the data flow is more complex. So everything needs to come from the cache, the weights, the inputs, and the partial sums, they can move from one processing element to the other to do the accumulation, but eventually they still need to go to the cache. And again, there are some examples, and I'm going to share these slides with everyone. So the contribution now of this paper and of Vivian Z. So there are really two contributions, and in some sense, the first contribution is more important. So the first contribution is what we talked about until now, which is to have a way to look at a large number of accelerators. And each of those accelerators, in some sense, probably was like I was telling you at the beginning. We designed this chip, and it works this well, and it has this energy, whatever. What she did is kind of dissect the concepts and put them in a common framework, this taxonomy, and then say, this accelerator has this data flow, this other accelerator has that data flow. And of course, this is how you really have an impactful paper. Probably if you look at this paper, I'm sure it has many thousands of citations, this IRIS paper. Again, if you have a good understanding of the problem and you can explain what other people have done, in principle, then you are able to say, okay, how can I improve on what those other people have done? And basically, she improves by coming up with this concept, which is not weight stationary, not input, not output stationary. She calls it row stationary. And the advantage, again, is that this is more of a global optimization. So again, if we go back to the slides that I showed until now, each of those solutions said, okay, now I'm saving the energy because of the weights. Now I'm saving the energy because of the partial sums. With this row stationary, she claims that it's a more balanced savings. It's not just one aspect, but multiple. So this is basically what she means by row stationary. It's basically taking one row. So again, for example, one previous data flow would have taken maybe just one element, one weight in the kernel. But what she takes one row in the kernel and one row in the input image, and basically loads, a part of them in the register file, and then that becomes stationary at that point, because now she can do this partial sum inside without having to go outside. So the idea is you need to multiply, one pixel with one weight, another pixel with the other weight, another pixel with the other weight, and add everything together. So that's kind of the MAC. And if she does this row stationary, everything happens inside the PE, all those. So you can see kind of where the savings come from. Nothing needs to go out for, you know, a number of these computations. So that's the bottom line. And basically, you know, you get this, you know, with one row, you get, you know, one row on the output. So that's kind of the, and you know, in retrospect, you will see, I mean, you probably have seen this already, but if you haven't seen this already, this probably, well, maybe it's going to be surprising to some of you, but many good ideas, really good ideas, many, you know, really innovative ideas, many impactful ideas are really simple in retrospect. You know, once someone comes up with that idea, many times it's incredibly, you know, you can say, well, you know, anyone could have done that. Well, no. It's simple in retrospect. Things that are simple in you know, it's like a diode somehow. You know, ideas are like a diode. You know, once they go past, you know, from the you know, anode to the cathode, you know, they are easy, but you know, going backwards is not easy. Yeah, so this is again, in retrospect, a very simple idea, but yeah, so that's basically how this goes. And again, the advantage is that you kind of maximize this, you know, a convolution. And, you know, to get back to the question from the, you know, online audience, again, this is still just about optimizing convolutional layers. It doesn't mean it cannot compute fully connected layers, but, you know, it's, you know, it's targeting convolutional layers. And yeah, so it's also, yeah, it's maximizing this accumulation in the register file. Any questions about this? Yeah, so, and there are, you know, now there are going to be examples of, you know, how that maps to, you know, to the array that we had at the beginning. So basically, you know, you saw how one row, you know, row stationary, how the computation happens. Now, when you have a kernel or a filter with, you know, that's two-dimensional, then, you know, the different rows would map to various processors in the array. And again, here at the bottom, you kind of see how, you know, you have the filter and you have some part of the, again, everything is kind of based on these rows. So you kind of have the first n rows of the image, and you get the first row of the output image, okay? Any questions about this? Okay. So, yeah, and you keep doing that, and basically you get your full output from the array. And again, this will answer the question, you know, about how does the data move left, right. But again, this is just one type of data flow. So in other data flows, it would move in a very different way. But in this specific way, and for this specific example, it moves that way. And again, here it shows how the row, the kernel, the filter rows are reused, and how the image rows are used. And again, here the reuse is diagonal. So, yeah. And the partial sums basically accumulate like this vertically. So, and now it's going to get a little bit hairy, and I'm not going to spend too much time because, you know, you can do this kind of on your own, and it becomes, like I said, a little bit complicated because now, you know, we looked at just, you know, one image and one filter, one kernel. But like we saw before, you have multiple images, and multiple means hundreds, thousands, millions maybe, and you have multiple kernels, again tens of kernels, and what you want is now to optimize even that part, and again you can take multiple images and concatenate their rows and do optimize that. Again, it becomes relatively complicated. I don't think I want to get too much into details here. You can also interleave kernels for the same row, basically in an image, and yeah, and then your partial sums get interleaved. So yes.
Different kernels at a time at different rows.
Say that again. So. Well, so here you have different kernels. So basically here you have two kernels. So yeah, you cannot see, it's light green and dark green. So basically the idea is, and again, this is about optimizing, kind of at the, so until now we talked about how to optimize the data flow for, one kernel with one image. But when you have multiple kernels and multiple images, you get an additional element of optimization because, for example, for the first row of the image, you can keep it, stationary, so to speak. And then you can have multiple kernels, and you get in this way, you get a reuse of this filter. And again, here it shows exactly what you are asking, which is two separate kernels with just one row of the image. And in the previous, here you had one row of a kernel with two different images. So, and again, each of these would give you a different type of optimization. And that's why I said it's a little bit, and here is where you have, two kernels and two images, and you kind of interleave them, I guess, that way. So, and so let's see, what's the difference between this? Oh, here it also shows how you interleave both the kernels and the images. So, yeah. And I guess here is where you put kind of everything together. And like I said, it gets complicated. You really cannot just look at this and figure it out. You kind of need to sit down with pencil and paper and kind of understand how this goes. But again, the idea is that you really need to map multiple images, multiple filters, and multiple channels kind of on the same hardware. And I guess the main point here is that this will provide you the maximum optimization. And the maximum optimization, again, remember, is for all these P's to be always doing a useful computation. So that's kind of the bottom line. As long as all of these P's do useful computation, you are good from a performance perspective, but it's true that from an energy perspective, it will depend on how you do this. Yeah.
Yeah. So I can see that the row 1 has been fetched 3 times into this, the second row of P elements. So is it like, are we fetching them 3 times from the global buffer, or they have been communicated with from the
Yeah.
first P to the rest of
Yeah,
the
yeah.
Ps?
Yeah. No, you only fetch them once. That's the point of this discussion. So, when it says here, the kernel rows are reused horizontally.
Correct.
What that means is that when you bring it from but again, this is relatively tricky. Again, you need to keep track. But when you bring them from the buffer or even from the main memory, you bring them just to one of them, and then you propagate them, right? Yeah. And same thing here, where again, the fact that the image, the fact that these are diagonally the same and these are diagonally the same also means that you only, so that's what it means when you do this, yeah.
That's how they are achieving the efficiency.
Yeah, exactly. See that? Oh, the question, okay. Is it beneficial to add a tension mechanism in CNN before input data? Okay, so that's a tricky question. So one, attention, we did talk about attention, I think 2 lectures ago, in the context, or maybe yesterday, in the context of recurrent neural networks. And attention also, is the workhorse of transformers. Attention for CNNs is not, I guess so attention is really useful for sequential, data, like language, where you want to have some connection, for example, in the case of language, between words, let's say in a sentence or in a story, actually, or in it could be a whole book, right? So a character that was introduced in the beginning of the book, there needs to be some way to access that information when you get close to the end of the book, right? And you know that some books, some movies, some are so complicated that for us humans, it's actually very hard to keep up, with all the characters and so attention kind of, that's the role of attention, is kind of making these connections across, time. In principle, I guess there could be aspects in image processing where you definitely could take advantage of attention. So, for example, if there are things, in different corners of an image that somehow are related and you want to understand something, but those are beyond these very simple, kind of basic CNN applications, which are, classification. Is there a cat or is there no cat? So I would say the answer to the question is basically not really. You would not really want or need attention for something like this. But yeah, I'll qualify that by saying that who knows. So this is basically kind of putting everything together with all these things. And now, right now it's not going to be maybe that interesting, but it shouldn't come as a surprise. Basically, when you compare these, weight stationary and output stationary, and then the row stationary wins. And I think it's kind of interesting to see why it wins in terms, and again, maybe this is not going to be surprising, but here is kind of a dissection of where the energy is going for these different types of data flows. And the light blue is the main memory, the DRAM, the cache memory is here, the register file is here. There is this network on chip, which is basically the interconnect, and the ALU is at the top. As you see, so maybe let's discuss, things that maybe shouldn't be as a surprise. So one is, I mentioned that it's to keep the ALU always busy for performance, right? And maybe this shouldn't be surprising, but that's a good sign. All of these things do, probably the output would come from all of these kind of at the same time, based on the fact that the ALU part is exactly the same for all of them. So that means that, in some sense, the processing is used, efficiently. But again, because we know that that's just one versus, tens or hundreds of units, in some sense, that's the least important part. And now, many of these, again, shouldn't be surprising. So the one that doesn't have a register file, doesn't have a register file of energy. But of course, the memory, accessing the main memory is, kind of killing it the most. So this shouldn't be surprising, but, this is kind of proof. Now for the wait stationary, for the wait stationary, they have much more DRAM and frankly DRAM and cache consumption. I'm not sure that I fully get that, but definitely the register file is underutilized. And in some sense, that's the trade-off. And the register file is underutilized because you bring the weights once, but then the partial sums are not using the register file. So it's kind of an expensive thing that way. On the other hand, the ones that have output stationary. So output stationary, remember, means that the partial sum accumulates in the register file, have a higher register file than the wait stationary. And that means that there's going to be more savings in the main memory. And again, this row stationary that she's proposing has, very low main memory. And I think I said main memory here. So here is the cache. I made a mistake, obviously. So this is the main memory. There is very little, cache, but again, here the register file is kind of overutilized. But overall, again, at least based on the assumptions that were made in that paper, it gets, the lowest energy. And now if you look at, again, which of these, the inputs, the weights, or the outputs, again, the row stationary wins. And there was the question about the fully connected layer. So here is the result for the fully connected layer. For the fully connected layer, because you don't have filters or kernels anymore, again, you have less from the the inputs and the outputs, and you have much more from the weights themselves, because a fully connected layer has many more weights. It's this multiplicative effect of the weights. And now, and we are almost done, so that's good, just in time for lunch. So in terms of, and again, this is the answering the question with convolutional and fully connected. So for convolutional layers, and this is now just for the row stationary. This is for her own solution. Again, we already know that the register file dominates the energy. And again, this is based on the AlexNet, I think, model. So again, different layers, because of the different sizes for the kernels and different number of kernels, have different energy consumption. For the fully connected layer, and in many ways, because the optimization of this architecture is for convolutional layers, for the fully connected layers, the DRAM dominates, because again, like I said, you can compute anything with this general architecture, but it's not going to be optimized. So the DRAM dominates for fully connected, but still overall is just 20%. So you still win overall, sorry. So this is a little bit, so in addition to, and now, there are some numbers here. So it's a 14 by 12 array. Now, don't ask me why 14 by 12, seems a little bit arbitrary, but that's how, again, remember I mentioned that designing something is about optimizing. So probably she started with some area and, whatever fit in that area. But then you have, the cache, and then you have, you also need to have the full, neural network. You need the nonlinearity, the activation function. So there is this ReLU, and there are some ways to put the image together and to break it apart, I guess. And again, TSMC 65 nanometer, some numbers there, runs at a few hundred megahertz, tens of giga operations per second. The precision is 6-bit fixed point, and the shapes of the kernels. So you can have anything between 1 and 32, 112 height. The number of filters, the number of channels. And the stride. We didn't talk about stride, but it's basically how, if you move the kernel or the filter 1 pixel at a time over the image, or if you jump over the image. So it can be anything between, and so there's a horizontal stride and a vertical stride. And yeah, so these are the results for yes.
When you want to, how do you exactly implement any sort of activation function like sigmoid ReLU on chip that without going out?
No. Yeah, so no. So she made this decision that is not going to be that general purpose. ReLU is the standard activation function for, for anything nowadays, pretty much. I mean, there are situations where there are other types of activation functions, but, ReLU has the advantage of being extremely simple. Anything negative, you make it 0. Anything positive, you just pass it. So, hardware, software, no matter how you implement, that's the simplest. All the other ones, sigmoid, all these things, they are, much more complicated on a computer, in hardware, and you don't get enough advantage. Again, I told you, design is all about trade-offs. The trade-off here is that you have something very simple that works well enough. There are cases where, people are, when you need different, so, they are talking about GELU and, there are non, ReLU, but again, for this is still a kind of a simple, simple solution, low power to be deployed at the edge. So yeah, she didn't even consider using anything else.
AlexNet, what activation function does it use?
I think it's using ReLU. I may be wrong, but I think it's you. It may have used something else. Again, yeah. So
The concern is basically if AlexNet in its fully connected layer, let's say doesn't use ReLU and uses some sigmoid function, then for that you have to get out of the chip and that will again cause a
No. Well, so AlexNet, yeah, I don't know the original AlexNet, that they published. You can take that AlexNet and, change the activation function and retrain it, and, it will work very well. So I'm sure when you say AlexNet, it doesn't really mean that you take the thing that they published in 2014 or whenever, and you just, don't touch it. It means, okay, I'm going to use kind of the same size kernel, but, you can, and you should actually consider changing, things like the activation function or, yeah.